Lesson 5.1 activities. Question 1, is lambda equals 4 an eigenvalue of this matrix? If so, find one corresponding eigenvector. Okay, so the way you determine if a scalar is an eigenvalue of a matrix is that you check, does the matrix times a vector equal the eigenvalue times the vector? If this has a solution, if there is a vector x that makes this true, then the lambda value is an eigenvalue. Okay, so to solve this, I would subtract 4x from both sides, so I get ax minus 4x equals 0. Factor out the x, so we get a minus 4I times x equals 0. All right, a minus 4I. So a is 3, 2, negative 3, 0, 3, 4, negative 1, 1, 5. Minus 4 times the identity. So the identity is the ones on the diagonal, the 3 by 3 identity. And if you multiply everything by 4, you're going to get 4, 0, 0, 0, 4, 0, 0, 0, 4. So whatever that is, I'm going to augment with 0, 0, 0 and solve this thing. Okay, so this equals, I'm just doing the subtraction here, no row reducing yet. 3 minus 4 is negative 1. And then 2, negative 3, 0. 3 minus 4 is negative 1. And 5 minus 4 is 1. So this right here, this is a minus 4I. And I'm setting it equal to 0. And so I row reduce. And we get 1, 0, 0, 0, 1, 0, 1, 1, 0, 0, 0, 0. So we don't have any rows that tell us 0 equals a number. This, in fact, has a free variable, so there are infinitely many solutions, which means lambda equals 4 is an eigenvalue. So just knowing that this is a consistent system is enough to say, yes, lambda equals 4 is an eigenvalue. But we also want to find one eigenvector, which means finding at least one solution to this system. So let's write it out. This says x1 plus x3 equals 0, and x2 plus x3 equals 0. Solve for the basic variables or the pivot variables. X2 is the opposite of x3. So I can pick any solution, anything that satisfies this would be an eigenvector. So x1, x2, x3. x3 I get to pick because it's a free variable, so let's make it 1. So that means x1 and x2 are both negative 1. So this is one eigenvector. There are infinitely many. And the answer is yes up here, because we can find a vector such that ax equals 4x. Okay, question 2 says find a basis for the eigenspace of the matrix A corresponding to each listed eigenvalue. So this is really two problems in one here. So I'm going to cut the page in half, and I'm going to do this twice. So I'm going to start with lambda equals 7. So find the eigenspace. That means find all the solutions to ax equals lambda x. So in the previous problem, we found one solution. The eigenspace is all the solutions. So I have to go through and do this solving process again. So A is 1, -4, -3, 5. And I have to subtract 7 times the identity. So 7, 0, 0, 7. And I'm going to augment that with 0, 0. That's solving A minus 7I times x equals 0. Okay, so do the subtraction, and I get 1 minus 7 is -6, -3, -4, 5 minus 7 is -2. Row reduce, and you get 1, 0, 0.5000. So translate this, and it says x1 plus 0.5 x2 equals 0. And any x1 and x2 that makes this true, all the x1s and x2s that make this true make up the eigenspace. So I'm going to solve for my pivot variable, my basic variable. So my eigenspace is all the vectors x1, x2, such that I'm going to put it in parametric vector form. X2 is my free variable. X1 is -0.5 x2, and x2 is free. So this is a description of the eigenspace. This is the eigenspace associated with lambda equals 7. They asked me to give a basis. So a basis for the eigenspace is just this vector 0.51. Okay, then I'm going to do the exact same process for lambda equals -1. So I need to solve ax equals lambda x for lambda equals -1. So I'm going to be solving a minus -1I times x equals 0. Okay, so a is 1, -4, -3, 5. Minus, I'm going to do -1 times the identity, so -1, 0, 0, -1, and I'm going to augment this with 0, 0. So 1 plus 1 is 2, -3, -4, 5 plus 1 is 6. Row reduce, and you get 1, 0, -1.5, 0, 0, 0. Okay, so translate this to equations, and it says x1 minus 1.5 x2 equals 0. Solve for the basic variable x1 in terms of the free variable x2. And then I can write out the solution. The set of all solutions to this is the eigenspace. Set up a vector for each free variable. x1 is 1.5 times x2, and x2 is free, so I just want this to say x2 equals x2. This is the eigenspace associated with lambda equals -1. I haven't quite I haven't given a basis yet. I've described the eigenspace, but it asks us to describe it by giving a basis. So the basis is a linearly independent spanning set. So 1.5, 1 is a spanning set because it's the only vector that has a weight on it when you add stuff together. So, and it's a single vector, so it's linearly independent. So my basis is just the vector 1.5, 1. Okay, so notice that the eigenvectors corresponding to the two distinct eigenvalues, meaning this eigenvector and this eigenvector. So I had two eigenvalues that produced different eigenvectors, and those two vectors, because one is not a multiple of the other, they are linearly independent. This exemplifies a theorem from 5.1 that says if you have distinct eigenvalues, different eigenvalues like -1 and 7, then they will produce linearly independent eigenvectors. Okay, next problem, matrix A. A theorem from 5.1 says that the eigenvalues of a triangular matrix, which matrix A is, are the entries on its main diagonal. So the theorem says that lambda should be 0, 3, and -2. I should have 3 lambda values. So let's try to justify this fact for the matrix A above. So note that lambda is an eigenvalue of the matrix A if there's a non-trivial solution to A minus lambda I times x equals 0. This is what we've been doing in the previous two problems, except that I gave you the lambda value, but this is the definition of an eigenvalue. Okay, if that's true, then lambda is an eigenvalue. Okay, so in this case, I'm trying to find lambda. So let's see what we can do. Find the matrix A minus lambda I. Okay, so A is 0, 0, 0, 0, 3, 0, 0, 4, -2. Lambda times the identity, the 3 by 3 identity, would be lambda 0, 0, 0, lambda 0, and 0, 0, lambda. So when you subtract, we get negative lambda, 3 minus lambda, 4, and -2 minus lambda. Okay, so to solve the equation A minus lambda I times x equals 0, you would augment A minus lambda I with zeros. So I'm just going to take the A minus lambda I that I calculated above, augment with zeros. So now you would row reduce, but since A minus lambda I is lower triangular, it's already in echelon form, right? It's not in reduced echelon form because the pivots aren't ones, but it's in echelon form. For the system to have a non-trivial solution, so any system AX equals 0 will always have the trivial solution. You can always make the variables x1, x2, x3 all zeros, and when you multiply anything by 0, you'll get the 0 on the right-hand side. So we always have the trivial solution. If you want to have more than one solution to a system of equations, that means you have infinitely many, which means that we need at least one free variable. So that means we must have at least one non-pivot column. So in order to have at least one non-pivot column, at least one of the diagonal entries of A minus lambda I has to be 0. So I'm going to set each diagonal entry of A minus lambda I equal to 0 and solve for the different lambdas. So I've got negative lambda equals 0, 3 minus lambda equals 0, or -2 minus lambda equals 0. So lambda equals 0, lambda equals 3, or lambda equals -2. Are your lambda values in part E, so these lambda values, are those the diagonal entries of matrix A? Let's scroll back up and look at A. Yes. 0, 3, and -2. Is matrix A invertible? Explain why or why not. We're going to use the invertible matrix theorem. So I'm just going to scroll up a little bit to look at A again. Here's my matrix A right here. So what you should notice in matrix A is that it has a column of zeros, which means that the columns can't be linearly independent. That column of zeros means that the columns are not linearly independent, they're linearly dependent, which means A is not invertible. No, because columns of A are linearly dependent. So this exemplifies another theorem from 5.1. It says that 0 is an eigenvalue if and only if A is not invertible. So we had an eigenvalue of 0. We can add this to the invertible matrix theorem. If you get an eigenvalue of 0, that tells you A is not invertible.